Earth's last ocean crisis. How acidification threatens coral reefs. The last ocean crisis. A warning for our future. Around 201 million years ago, the oceans became a battleground for survival. Acidification transformed them from vibrant nurseries of life into harbingers of extinction. New research from the University of St. Andrews and the University of Birmingham has revealed that a sudden and severe drop in ocean pH directly triggered one of Earth's most catastrophic mass extinctions. The culprit? A massive surge in atmospheric carbon dioxide. This groundbreaking study, the first to reconstruct ancient ocean pH using boron isotopes in fossil oysters, shows that the acidification at the Triassic-Jurassic boundary wasn't just intense, it was prolonged. During this period, marine life, including corals, ichthyosaurs, ammonites, and bivalves, thrived. But when the pH dropped, coral reefs vanished in a reef gap that lasted hundreds of thousands of years. This collapse reshaped marine ecosystems, reducing carbonate sedimentation and leaving many organisms unable to form shells or skeletons. Researchers analyzed oyster samples from Lavernock Point, Wales, to detect a 0.29 unit drop in ocean pH, possibly exceeding 0.41 units. This would equate to more than a doubling of atmospheric CO, with levels surpassing 1300 ppm. Today, CO levels hover near 420 ppm, but the study warns that such extreme conditions could recur. The acidification coincided with a sharp decline in carbon isotope ratios to the power of 1 cubed C, known as the main carbon isotope excursion, CIE. This suggests an enormous carbon release event, with estimates suggesting over 10,000 gigatons of carbon entering the system, primarily from Earth's mantle. Volcanic activity, as the supercontinent Pangaea fragmented, likely contributed to these emissions. The geological record shows that such co-surges transform the planet, acidifying oceans and triggering mass extinctions. Dr. James Ray, a co-author, emphasized, "We must act swiftly to prevent these outcomes in our future." Volcanoes and ocean acidification, a complex connection. Using the CGENIE model, researchers tested scenarios with varying carbon sources. The model confirmed that mantle-derived carbon was the primary contributor. While methane clathrates were initially thought to be the main cause, data suggested they may have played a lesser role. The study highlights that volcanic CO and contact metamorphism were key drivers. As carbonate saturation plummeted, marine life struggled, with shell-building organisms struggling to survive below safe thresholds. The initial drop hit harder. Interestingly, the more catastrophic acidification may have occurred earlier, during the initial CIE. Though no oyster samples span this exact period, data suggest the initial event was faster and potentially twice as intense in pH drop. This aligns with broader collapses in carbonate sedimentation and widespread marine die-offs. Ocean rebound, a slow healing. Despite the devastation, ocean pH eventually recovered. Around 201.28 million years ago, pH levels began rising again. This rebound may have been driven by the emergence of silica-producing organisms, which disrupted reverse weathering, a process that had previously locked alkalinity in clays, prolonging high CO, low pH conditions. Its sudden stop helped restore ocean chemistry. History warnings, a call to action. Dr. Sarah Green, a co-author, notes, the Triassic-Jurassic mass extinction lasted much longer than today's acidification, which occurs at a much quicker pace. The study warns that current CO levels, if left unchecked, could reach levels seen during past extinctions. This isn't just a historical event, it's a warning for our time, she adds. Ocean acidification, a global threat. The study confirms that acidification has now occurred in 3 of Earth's 5 major mass extinctions, Permian Triassic, Torsion, and Triassic-Jurassic. These events, each marked by massive CO releases, show that even natural sources can trigger oceanic catastrophe. Today, the same process is unfolding rapidly, with the past offering no comfort. The urgency of action is clear. A future worth preparing for. The Triassic-Jurassic event teaches us that prolonged co-release, even from natural causes, can destabilize the planet's systems. Today, we face a similar challenge, but at an accelerated pace. The lessons of history are unambiguous. We must act now to mitigate climate change and protect our oceans. Published in Nature Communications, this study underscores the critical role of ocean chemistry in shaping life's fate. As Earth continues to change, the choices we make today will determine the legacy of our planet for generations to come. Scientists reveal what decimated marine life 200 million years ago. Researchers uncover the devastating cause behind 200-million-year-old marine extinction. A revolutionary new investigation published in Nature Communications has revealed crucial information about our planet's ancient history, illuminating the devastating catastrophe that triggered widespread marine extinction during the Triassic-Jurassic transition approximately 201 million years ago. This groundbreaking research, conducted by scientific teams from the universities of St. Andrews and Birmingham, establishes a direct connection between the mass die-off and ocean acidification caused by massive volcanic carbon dioxide releases. These discoveries not only illuminate Earth's distant geological past, but also provide essential perspective for addressing contemporary climate issues. Through examination of preserved oyster remains and application of cutting-edge methodologies including boron isotope measurement, the scientific team reconstructed ancient oceanic pH levels during this pivotal time period, demonstrating the unprecedented speed and intensity of environmental transformation. The ramifications of these findings extend far beyond academic interest, serving as a powerful cautionary tale about our ocean's future. The devastating impact of volcanic carbon dioxide on ancient oceans. The investigation's most significant revelation identifies massive volcanic eruptions as the primary catalyst for this extinction event through their release of enormous quantities of carbon dioxide into the atmosphere, ultimately causing severe ocean acidification. This dramatic CO2 surge likely coincided with the initial fragmentation of the supercontinent Pangaea, triggering widespread volcanic activity. Consequently, Earth's oceans experienced a dramatic pH reduction exceeding 0.3 units, with some research suggesting potentially greater declines. While this numerical change might appear modest, even subtle alterations in ocean chemistry can devastate marine ecosystems. For sea creatures such as mollusks, coral formations, and microscopic plankton, all dependent on calcium carbonate for skeletal and shell development, this acidification proved catastrophic. But here's where it gets truly alarming: the implications for our modern world couldn't be clearer. Dr. James Ray, who co-authored the study and conducts research at the University of St. Andrews, highlighted the profound significance of their findings. The geological record tells us that major CO2 release transforms the face of our planet, acidifying the ocean and causing mass extinction, he explained. This research emphasizes a disturbing truth: rapid carbon dioxide increases fundamentally alter oceanic chemistry, disrupting global ecosystems with devastating consequences. Rapid environmental change, historical precedent versus contemporary crisis. Perhaps the most concerning aspect of this research is the comparison between ancient acidification rates and the velocity of modern oceanic changes. Dr. Sarah Green, Associate Professor of Paleoclimates at Birmingham University, emphasized that while the Triassic-Jurassic extinction unfolded across thousands of years, contemporary ocean acidification is progressing at an unprecedented pace. This modern acceleration stems primarily from human activities, particularly fossil fuel consumption and forest clearing. The mass extinction event during the Triassic-Jurassic period was over a much longer timeframe, whereas modern ocean acidification is happening at a much quicker rate, Dr. Green elaborated. This accelerated timeline provides marine organisms significantly less adaptation opportunity, making ecosystem recovery substantially more challenging. The reef gap, documented in fossil evidence, A prolonged interval during which coral formations completely disappeared, requiring hundreds of millennia to re-establish, illustrates the enduring consequences such events inflict on marine biodiversity. And this is the part most people miss. Today's situation could potentially be worse. If carbon emissions continue their current trajectory, we face an even more rapid and devastating decline in oceanic health. This underscores the urgent necessity for immediate climate action and carbon reduction strategies to prevent repeating, or exceeding, ancient catastrophes. Ancient remains, decoding Earth's prehistoric oceanic conditions. The research team utilized fossilized evidence to reconstruct the environmental circumstances precipitating this extinction event. Researchers concentrated specifically on ancient oyster shell remains, which preserve chemical signatures revealing historical ocean conditions. By examining boron isotope compositions within these shells, scientists directly reconstructed oceanic pH levels during the critical Triassic-Jurassic boundary period. This innovative approach, never previously applied to this geological transition, delivered the most definitive evidence yet regarding the magnitude and rapidity of ocean acidification during this crucial time frame. The preserved oyster remains not only confirmed dramatic acidification, but also revealed long-term ecosystem impacts. Oceans recovered slowly from this pH decline, with coral formations vanishing from fossil records for hundreds of thousands of years. This extended reef gap demonstrates how profoundly and persistently marine life suffered from the massive carbon influx. This fossil evidence emphasizes a critical lesson: when oceanic chemistry undergoes such extensive alteration, recovery proceeds slowly, and ecosystems experience prolonged disruption. As the research suggests, contemporary oceans could suffer similar long-term damage if current environmental trends continue unchecked. What do you think about these findings? Do they change your perspective on modern climate action? Is humanity doing enough to prevent history from repeating itself? Share your thoughts in the comments below. Do you believe we are headed toward a similar catastrophe, or can we change course in time? Volcanic winters. How eruptions helped dinosaurs dominate. A forgotten catastrophe from Earth's past changed everything, creating a pathway for the dinosaurs' meteoric rise. But here's where it gets controversial. It wasn't just a single disaster, but a relentless barrage of volcanic winters that reshaped the planet forever. Curious how this disaster unfolded? Let's dig into the details and understand why this event still sparks debate among scientists and armchair historians alike. Let's set the stage. Have you ever wondered why dinosaurs became the dominant force on Earth? Well, more than 200 million years ago, our planet suffered through a series of colossal volcanic eruptions, so powerful that they blanketed the sky with ash and gas. Imagine years of sunlight dimming under an ashen haze. These conditions triggered a profound planetary cooling, a phenomenon scientists now call a volcanic winter. According to a recent study, this chain reaction led to a mass extinction that unintentionally opened the door for dinosaurs to take over. Fascinated yet? This is where history gets dramatic. So, what really transpired at the end of the Triassic period? Roughly 201 million years ago, the Triassic era drew to a close. During this time, more than 70% of all land species vanished. With so many competitors wiped out, dinosaurs found themselves at a massive advantage. They seized their moment, flourished, and soon became the undisputed rulers of the Jurassic. But the question persists: what triggered such a sweeping extinction? For decades, experts pointed to the massive volcanic region known as the Central Atlantic Magmatic Province (CAMP). Picture all the continents fused into one supercontinent, Pangaea, the backdrop for this cataclysmic activity. Yet, the finer details remained unclear until now. So, what new light did scientists shed on this mystery? A dedicated team scrutinized ancient volcanic rocks from places as far-flung as Morocco and Canada. These rocks held clues in the form of tiny records of Earth's magnetic field, helping researchers pinpoint the timing of ancient eruptions. Their investigation revealed a shocking finding: not one, but 5 gigantic eruptions erupted within a mere 50,000 years, a blink in Earth's long timeline. Even more striking, each burst lasted less than a century. Can you grasp how rapid and relentless that is, geologically speaking? During these turbulent episodes, volcanic plumes hurled vast amounts of sulfur dioxide high into the atmosphere. This gas acted almost like a planetary sunshade, scattering and reflecting sunlight away. The result? A drastic, sudden drop in Earth's temperatures, what scientists label a volcanic winter. But why was this such a deadly recipe? The unexpected chill stifled plants' ability to perform photosynthesis. With sunlight blocked, plants withered. In this domino effect, animals grazed into starvation, and carnivores followed. Entire food webs crumbled. And here's the shocker. A single volcanic burst released an estimated 63,000 megatons of sulfur dioxide, over 500 times more than the famous 1783 Laki eruption in Iceland. Because the eruptions happened in relentless succession, ecosystems never had a chance to recover. The oceans faced a crisis of their own, albeit for different reasons. Here, volcanic carbon dioxide dissolved into the water, warming it, making it more acidic, and stealing precious oxygen. Marine life couldn't cope, and vast numbers of aquatic species went extinct. Think about it, land animals perished from freezing and famine, while sea creatures succumbed to heat and suffocation, all from the same eruptions. Is it surprising that this single event so profoundly altered life on Earth? And what about the dinosaurs themselves? Dinosaurs were already present before these apocalyptic winters, but they lived in the shadow of other dominant species. Once the volcanic onslaught cleared the field, dinosaurs moved in, able to thrive where their rivals could not. Many scientists now believe that smaller, feathered dinosaur species were especially well suited to survive the harsh, cold conditions, while larger, less adaptable reptiles perished. This single twist of fate propelled dinosaurs to reign supreme for the next 130 million years. Does this challenge your idea of their evolutionary destiny? So, what valuable lessons can we draw today? This research powerfully reminds us that Earth's climate can swing with scary speed, wiping out vast swaths of life and rewriting natural history in a geological instant. In less than 500 years, just a few human lifetimes, 5 brief, but extreme volcanic events changed the planet's entire trajectory. And here's another truth: catastrophic changes, while tragic, sometimes pave the way for new life to flourish. Without this ancient tragedy, the age of dinosaurs might never have happened. To uncover these secrets, scientists combined techniques like magnetism studies, soil analysis, and marine geology, reconstructing a lost world from scattered clues. Their efforts help us see how deeply intertwined life and climate have always been, whether in ancient times or today. And this is the part most people miss. Could such volcanic winters or swift climate upheavals threaten our planet's future once again? Do you agree that disaster breeds opportunity, or does nature go too far? Share your thoughts below. Do you see echoes of our current climate challenges in this ancient extinction event, or do you think the comparison goes too far? Let's keep this discussion going.